Assalamu alaikum and good morning everyone. In previous video we have discussed minimization example of assignment problem. In this video we'll be discussing maximization of assignment problem. So let's begin with the example. 5 salesmen are to be assigned to 5 districts. Estimate sales revenue in rupees 1000 for each salesman are given below. Find optimal assignment that maximize the sales revenue. Here the table is given and the question was asked in November 2020 of University of Mumbai. So here we can see 5 rows are given, 1, 2, 3, 4 and 5, and 5 columns are given, 1, 2, 3, 4 and 5. So let's begin with the solution. Check whether the given cost matrix is balanced or unbalanced. Balanced means number of rows and columns are equal. Unbalanced means number of rows and columns are not equal. In this example, we can see the cost matrix is balanced. Here the number of rows and number of columns are 5. Since we are to maximize the sales revenue, we need to convert into minimization form before applying the Hungarian method. For this, we obtain the opportunity loss matrix, that is called as a cost matrix, by subtracting each and every element from the table from the largest element in it, that is a 41. So each entry we have to subtract from 41 to convert the maximization example into minimization for applying Hungarian method. Thus we obtain the given matrix. 41 is subtracted from each and every entries of the table. So new matrix we got 9, 3, 1, 13, 1, 1, 17, 13, 25, 0, 14, 8, 11, 4, 19, 3, 0, 5, 5, 12, 8, 1, 6, 2. Here is my resulting matrix. In this matrix, we are going to perform all the operations of Hungarian method. So second step, we are having the row minimization. Locate the smallest element from each row of cost matrix and subtract every element from smallest element of that row. As we have done in the previous example, the steps are common, just we have to convert the maximization example into minimization so as to apply Hungarian method. So as we can see in first row the minimum value is 1, in second row minimum value is 1, in third row minimum value is 0, in fourth row minimum value is 0, and fifth row minimum value is 1. From that all values we have to subtract each and every entries. So resulting matrix we got as 8 2 0 12 0 first row, 0 16 12 19 4, 0 14 8 11 4, 19 3 0 5 5, 11 7 0 5 1. So here is my step 2 of row minimization. Step 3, column minimization. On the updated matrix, on the resulting cost matrix, we have to perform column minimization. So here we can see in first column the minimum value is 0, second column minimum value is 2, third column minimum is 0, fourth column minimum is 5, and fifth column minimum is 0. From each entries of the column we have to subtract the minimum entry. So we can see the resulting matrix we got for column minimization. Now using this resulting matrix we are going to search for the optimum solution. So what the conditions are given, they examine the row successively until a row with exactly one zero is found. Draw a rectangle around this zero as given and cross out all other zeros in the corresponding column. Proceed in this manner until all the rows have been examined. If there is more than one zero in any row, do not touch that row, pass on the next row. Same step we have to apply for the column also. So here we can see the assignment process. We're going to see the row wise. First we're going to examine row wise. As we can see in first column, in first row we are having more than one zero, we're going to skip that row. In second row we can see we are having only one zero, we're going to examine that row and we have to allocate that zero. Since we are examining row wise, we have to cancel all the column entries. In second row we can see there is no 0. In fourth row we can see we are having more than 1 0, we're going to skip that row. In fifth row we are having more than 1 0, again we're going to skip that row. Same process we have to do for the column. Now column wise we can see we are having only 1 0, we're going to assign that 0 and we're going to cancel out all other entries from the row. From third column we can see we are having more than 1 0, and for the fourth column again we are having more than 1 0. Now what does step C states? If a row or column of the reduced matrix contain more than 1 0, arbitrarily choose a row or column having minimum number of zeros. Arbitrarily select any 0 in the row or column, choose and draw a rectangle around it and cross out all zeros in the corresponding row and column. As we can see we are still having the number of 0, we randomly will going to assign the 0 and we're going to cancel out all other entries from the row. Similarly, we're going to assign at the last one and we're going to cancel out all other entries from the row. Here we can see the number of lines 1, 2, 3 and 4. Number of lines are 4 and order of matrix is 5, which is not equal, which means the given solution is not optimal. So same step we have to apply for the resulting matrix to find the optimum solution. So we have to revise the cost matrix as follows. Find the smallest element not covered by any lines. Subtract this from all the uncovered elements and add it to elements at the intersection of the two lines. Other elements covered by the lines remain unchanged. Repeat this procedure until an optimum solution is formed. So on the existing matrix, first we're going to see the minimum element from uncovered entry is 4. As we can see, the elements which are not covered by the lines, among that the minimum entry is 4. That 4 we have to subtract from all uncovered entries and we have to add at the intersection of the lines. Minimum entry was 4, so we're going to add 4 at the intersection of line and we're going to subtract from 4 from all uncovered entries. So we can see 12 0 0 7 0 0 10 8 10 0 08420 23. This was the intersection of lines, so it become 23. 8 was the intersection of the line, it become 12. 11 was the intersection of line, it becomes 15. And all other entries from the first row 0070 remain unchanged. 14 was the uncovered entry, so it become 10. 12 was the uncovered entry, it become 8. Similarly 12, 14, 4, 8, 6, 4, these are the uncovered entries, so we have subtracted value from all these entries, and 1005 and 5001, these are the covered by the lines, so remain unchanged. Now step for the optimum solution. In first row we can see number of zeros are more than 1, so we're going to skip that row. In second row again more than 1 0, third row more than 1 0, fourth row more than 1 0, fifth row more than 1 0. Same analysis we're going to do for the column. In first column we are having more than 1 0, we're going to skip that part. In second column we are having more than 1 0, so we're going to cancel out the entries. In third column we're going to have the number of zeros more than 1 0. In fourth column again more than 1 0. In fifth column again more than 1 0. So randomly we're going to assign the values. Here we're going to assign the 0, the part is get cancel out. Next we're going to assign the 0, the part is get cancel out. Again we're going to assign the 0, the part is get cancel out. Again we're going to assign the 0 and part is get cancel out. So just remember that each entry should get a single allocation. Each resources will get only one activity. Not more than one activity will be assigned to any other resources. So in this way we have formed the allocation. Now we can see the number of lines and order of matrix is 5. The solution is optimal. So we're going to assign the salesman in the district. A is assigned to 2, B is assigned to 1. How are we going to form this district? Wherever we have drawn the square, that will going to assign. 1 will be assigned to B, 2 will be assigned to A, 3 will be assigned to E, 4 will be assigned to C, and 5th will be assigned to D. So in this way we got the assignment. So maximum sales revenue was 1,91,000. All add all those entries 38, 40, 37, 41, 35. So we got 191. Says all the entries are given in terms of thousands. So final answer is 1,91,000.